Alright, I'm going to take a look at what's called Full Mill Theorem Calculus Part 2. And it basically talks about the operation of taking the derivative versus the operation of integrating. So let's take a look at an example. This means I'm going to take the derivative of what's ever in here, okay, with respect to x. So if I had x squared, I would get 2x as my answer. Okay, so I'm just taking the derivative of that. And what I'm going to put in here is I'm going to put an accumulative function in here. And so what I'm going to get is integrate from 4 to x 2x dx. Oh, excuse me, I don't want to do that. Let's see if I can delete that. dt, where these values got to be different. dt, 2t dt. So if I'm just going to do this part right here, you know, it's inside brackets, I'm going to do it first. This means I got to find the antiderivative, which is t squared, and I'm going to evaluate it from x to 4, and I'm going to get x squared minus 4 squared, which is x squared minus 16. Again, this is the antiderivative with b in it minus the antiderivative with a in it. Alright, so that's what I'm taking the derivative of. So now if I'm going to replace this integral with the cumulative function, which is x squared minus 16, and I'm going to take the derivative of that with respect to x. Well, if I do that, the derivative of x squared is 2x, derivative of minus 16 is 0, and I get this as my answer. Well, how did that relate with what I started with? Well, it looks like all that happened was x replaced t. Well, let's take a look at another example. Let's take a look, and I'm going to take the derivative. I'm going to integrate from negative 1 to x of t to the third minus 2t plus 5 dt. I'm going to take the derivative of that with respect to x. Now, I'm thinking, based on my last experience, maybe I'll get x cubed minus 2x plus 5 as my answer. And I could skip all this work and go directly from this, because this derivative and this integral kind of cancel out, and all I got to do is this direct substitution. Well, let's see. Well, I'm first going to integrate, and I'm going to have 1/4 t to the 4th minus t squared plus 5t, and I'm going to place 5x in it first, and then negative 1, and I'm going to have 1/4 x to the 4th minus x squared plus 5x, okay, minus some constant, and it's going to be 1/4 minus 1 minus 5, and so this is going to give me a negative 6/4, so it's going to be plus 6 1/4. In here I'm going to have 1/4 x to the 4th minus x squared plus 5x. Okay, and now I'm going to take the derivative of this, because that's this outer thing. Well, this is going to go to 0, isn't it? And so I'm going to use the power rule on the rest of these. I'll write it over here, and I'll get x cubed minus 2x plus 5. Ha! Lo and behold, that's what I have up here. So let me delete this one more time. Well, what if I got, take the derivative of, with respect to x, something crazy that I can't even take the antiderivative of. 3 to x of the sine of t plus e to the t dt with respect to x. Well, the fundamental theorem of calculus says all I got to do is take this baby in, and I'll get the sine of x plus e of the x. Okay? And so the students are saying, hey, that's not too bad. Well, what if I have something like this? X squared. And again, let's do something easy. Let's take 2t dt, and I'm going to take the derivative of that. Because, you know, this is just not plain x. So I'm going to integrate this. And the antiderivative is t squared, and I'm going to put x squared in here, and I'm going to put 3 in here. And I'm going to get x squared minus 3 squared, and I'm going to get x to the 4th minus 9. Let's see if I did that right. And so when I take the derivative of this, dx, I'm going to get 4x cubed, right? Well, that doesn't quite look right, does it? Well, this is really, let's take a look at this, what this 4x cubed really is. This is the same as x squared times 2, right? Remember, this was going to go into here. So I get 2x squared times 2x. Well, where does this 2x come from? Well, that's the derivative of x squared. So what really this is an application of the chain rule. Let me show you what I mean by that. I'm going to again use the shortcut. I'm going to use the fundamental theorem of calculus part 2. And I'm going to integrate from 0 to x cubed, the cosine of t dt. And I'm going to take the derivative of that with respect to x. Well, what I should get is the cosine of x cubed, I do, okay, times, now the chain rule says I need the derivative of that, which is 3x squared. So my answer is 3x squared times the cosine of x cubed. And what I was doing before, the reason I didn't have that was when I had something like this, derivative of 0 to x, that's a 0, cosine of t dt, with respect to x, I'm going to get the cosine of x, but what's the derivative of x using the chain rule? It's 1, so you don't see it. So all you need to do is do direct substitution in for this value. Usually it's t, but it doesn't have to be. And if it's something other than x, you're going to have to continue on with the chain rule. I'm going to do one more. I'm going to take the derivative of, and I'm going to integrate from pi to 2x of the secant squared of t dt with respect to x. I'm going to take that derivative. And so my answer is going to be the secant squared of 2x times the derivative of what's inside here, 2, or 2 secant squared of 2x. And that's my answer.